Thank you for the introduction. This project was done in cooperation with a company called Tesla Networks. Just to be clear, it's not the cars, so it's not Elon Musk that came to us, it was somebody else, a guy called Bart Penn. He came to us with a question, and he wanted to make a retrofittable sensor that you could basically attach to any kind of drinking bowl to monitor your horse and to know if it was still drinking. Now, why would you actually want to know if your horse was still drinking? Now, a lot of horses are bought for sports or for recreation or as pets. So in general, you want your horse to be healthy. If your horse stops drinking, that is one of the first signs that your horse could be ill. Dehydration itself adds to the symptoms. But it could also mean that your horse has colic, and colic is usually abdominal pain, and abdominal pain usually means something is quite life-threatening that's going on with your horse, something quite significant. The kind of environment that you want to monitor your horse are twofold. So I've got two nice pictures of a horse here. One is in a meadow and one is in a stable. And these two pictures actually illustrate the design requirements for such a sensor quite well. The first of which is there is no power available. There's no power plug in a stable, and there's definitely not a power plug in a meadow. So this means our application needs to be battery powered. If an application is battery powered, this also means that you want it to be as low power as possible, so you don't have to go change batteries every few weeks or every few months. You want it to last preferably a few years. The next one is actually quite simple as well. You see two shapes of drinking bowls, but you have a lot more shapes. So the way you want to attach something, it's quite difficult to create something that you can attach to anything. For this purpose, we have chosen something that's flexible and that you can glue. The last thing is you don't have a way of connectivity. There's no connectivity in stables or in meadows, so you want to send your data to a backend, which is quite common for an IoT application. For this purpose, we use an LPWAN solution. This slide actually actuates the problem of all the kinds of drinking bowls a bit more. As you can see, like the top right one is a bit exotic in shape. It's not that simple to just dump a sensor into that. So just to summarize the design requirements, it needs to be battery powered, as low power as possible. We need some kind of connectivity, and we need to be able to fit it in any kind of drinking bowl of any shape or any size. For that purpose, we've chosen to go with a flexible capacitor sensor. You can see the sawtooth structure, which is actually inspired by moisture sensors for soil, because they work quite well. And we chose to etch it on a flexible polyamide. Now, polyamide is a material that's used for flexible PCBs, most commonly in PCs and smartphone as the connector between two different PCBs that you can fold. And it's very good for this application because it's very resistant to chemicals and impact. So it's very strong. You can pull on it. If the horse bumps into it, it's not a problem. And the way we designed it is that you can apply it like double-sided tape. Well, because the market that this is aimed at, those people are not technical. You know, you saw the drinking bowls. These people don't want to be taking a wrench to their drinking bowl and have to disassemble it. They want it to be simple to just stick in it. So basically the dad and his 16-year-old daughter can mount it themselves. That's why we chose the double-sided tape approach. Now, a typical setup would look like this. So usually your drinking bowl, you get a water supply pipe, and there's a kind of clapper that works as a switch. And when you press it, the bowl fills with water. Whenever the horse gets thirsty, it just presses the clapper, it gets water. The sensor gets just taped into it, and it doesn't really matter if it's to the left or to the right or to the bottom or to the top, because it's there's always a part that's just submerged, and when you add water to it, the capacitance of the sensor changes. As an IoT application, the system architecture is like this. The sensor gets pulled approximately every 15 seconds, and this sensor data is sent to the backend using LoRa. Why did we pick LoRa is because it's one of the rising LP1 technologies, but we most specifically used the crowdsourced the Things network. The Things network has a few advantages, which are you don't need a subscription fee, so you can just use it for free. If there is no coverage You can provide coverage by deploying your own gateway, which is added value for the company, because the company could just add a very low entrance cost for the customer, and he can create coverage wherever he needs to without having to make excessive costs. And lastly, LoRa is pretty low power as well, and it goes a very long range. There's research with line of sight that goes up to 50 to 100 kilometers. Now, we evaluated our sensor in twofold. We evaluated it in the lab, trying to determine how it behaves when you add water. And then we did an extensive measurement campaign for a few months where we actually deployed it in real stables and looked at how the sensor behaved when a horse drank. So first in the lab, it's quite, well, this is very obvious. You want to know how the capacitance changes when you add water to your drinking bowl, right? So when the bowl is dry, you can see that the capacitance is quite low, but as soon as you add a little bit of water, the capacitance rise is quite large. But after the initial water, the capacitance starts rising in a linear fashion for the same amount of water added. And this is interesting because it's the same for all the materials we tested it on. So we tested it in 2 aluminum drink bowls, a cast iron one, and a plastic one, which are the most common materials for these. Our measurement campaign was done in 2 stables in 2 different places. We always added 2 sets of electronics when we were measuring it for redundancy in case one broke, and also so we could compare the measured values to be sure that it was always working correctly and the way we expected. On the right picture, you can see our electronics, which are a prototype. It was powered by a low-power EFM M0 Plus microcontroller from Silicon Labs. If you put it to sleep, it has extremely low power consumption. The same with the LoRa module, which was provided by Microchip. Now, how does the sensor actually behave? I've taken a completely arbitrary window from our measurement campaign, and I tried to see what happened when the horse was drinking. So you can see all the spikes. That's when the horse drinks, and there's a very small spike as well. It's the one in green. That's also when the horse was drinking. In between, obviously, I checked, did the horse ever go to the drinking bowl to see if we got false positives or false negatives, and in all the data that we gathered, you couldn't see any false positive or false negative. Now, how you deal with the small spike is the easiest way to make an algorithm to detect if the horse was drinking was just to take the derivative, and the small spike is still large enough to easily detect horse drinking. Now, the last thing that we have to evaluate is power consumption. Now, imagine if we would send every LoRa message, every pole of the sensor, and we would send a message. You have 15 seconds of quiescent current, then you wake your sensor up, you pull your sensor, and then you send a LoRa message. You can see that the first one number on the graph is pulling your sensor, and then 2, 3, and 4 are all related to your LoRa message. 2 is sending your LoRa message, and then you get 2 receive windows where the backend acknowledges your message. You can see this takes a lot of power. Just to make it a bit more clear, if you look at the abstract bar graph, the LoRa message takes just so much more power than all the rest. So if we can optimize the amount of times we have to send, we can reduce our power consumption even further. And for this purpose, the LoRa packet is 222 bytes. Let's say that pulling our sensor takes 10 bits. This means you could use 2 bytes per sensor value, and you could leave a bit of space for metadata. You can now see that the LoRa message takes a lot less power compared to all the rest. And if we do this, we can, the battery will live a lot longer. Our goal was to make it live on 2 AA batteries for a couple of years, and we achieved this. So in general, we achieved all our goals. You can quite simply deploy it anywhere. It's low power, and our battery life is estimated, worst case, at 11 months. But this means that the LoRa always uses the highest spreading factor, so it has the longest time on air, and never receives its acknowledgement in the first receive window, which is quite significant for the power consumption. Best case, it's estimated at 14 years, but that means that your power is, your spreading factor is the lowest, and you always receive your acknowledged in the first window. So realistically, it'll be somewhere in the middle and it'll be a couple of years of battery life. We do have a bit of future work where we want to take the quality of life of the environment added to it, so that you add humidity and temperature. So when the horse is in the stable, you can always make sure that the environment is optimal. So far my talk, if there's any questions.
All right, thank you. Thank you.